So all right, we're going to do a small exercise on principal component analysis right now. Go to the directory in which the data is stored, and the directory I think is desktop. I'm so sorry, the directory is desktop. Usko band karo. CHE381 lab. Okay, let's just load the data. Load ls star.mat. What are the data files? PCA data, PCA data 2. We'll do it on 2 data sets. Okay, load PCA data. Over there, X and X test. Okay, X is the data on which you will build your model. X test is the data on which you will test whether it is following the same model or there is a breakdown of the correlation structure. All right, because PCA captures the correlation structure in the data, right? So all right, so you say, well, X is equal to X scaled. Just a second यार, ये साला कहाँ गया यार? Okay, okay, I'm going to scale the X data to be, for all the columns to be 0 mean and unit variance. Okay, so let's just see, m comma n is equal to size of X. Okay, m kitna hai? 200. There are 200 data points and there are 10 variables. Okay, so it's a 200 by 10 data matrix. Let's see, so X scaled is equal to X minus 1 m comma 1 star mean of X dot divided by 1 m comma 1 star standard deviation of X. Okay, this is the scale matrix. All right, so if I say, well, what is the mean of X scaled? 10 to the power minus 16, everything is 0. What is the standard deviation of X scaled? Everything is 1. All the columns have, so everything is now scaled. Influence of units, etc. is now gone. Okay, then I say do a singular value decomposition of the X matrix. So I'm going to get U, sigma and V as my output, SVD of XS. All right, SVD of XS. I'm doing the singular value decomposition of the scaled matrix. Okay, now I say, well, bar extract the diagonal elements of, अबे तो मैं क्या करूं, दिख नहीं रहा तो यार. So we have plotted the singular value. You can see only 3 singular values are significant. The rest, yeah, there is a big bump here. All this rest is insignificant actually. ये बात हजम हुई कि नहीं? हाँ? All right, so we are going to retain the first 3 principal components. The remainder we are going to reject. Okay, so what are the scores? Okay, T, the scores is equal to, okay, before I do this, I will also scale my test data, subtract the mean of X and divide by the standard deviation of X. All right, so X test scaled is equal to X test minus, just a sec, यार size of X test करेंगे 50 by 10. Okay, so X test scaled is equal to X test minus 150 comma 1 star mean of X, not mean of X test but mean of X. I am subtracting the mean of my nominal data and I am dividing by the standard deviation of my nominal data. Nominal data is X, not X test. dot divided by dot divide is element by element division. Once 50 comma 1 star standard deviation of x. So this is my test data, that's the xs is my scaled whatever training data. All right, so I say, well, t is equal to xs star projection onto what? The principal components. What are the principal components? The columns of V, the first three columns. I am retaining three principal components. So the first three columns of V matrix, the V matrix that has been obtained from SVD, singular value decomposition. So star V all comma the first three columns, right? These are my scores. All right. What will the error be? Error will be is equal to xs minus t star V all comma 1 to 3 transpose. PCA, what was it called? X equal to TP transpose plus E. So E is equal to X minus TP transpose. So that's what I've done, TV transpose. Right? So this I've gotten the error. ये बात हजम हुई कि नहीं? Hotelling's T square statistic is equal to okay, T star S to the power minus 2 star T transpose. Okay, so I've gotten the Hotelling's T square statistic. Okay, oh shit. For S1 to 3, the first three only, I have to extract of the singular of the sigma matrix only the first three columns and rows, right? Because I have retained only three principal components. So that I did not do, therefore this error message came in. So it's actually 1 to 3 comma 1 to 3. Yeah, so this is the Hotelling's T square statistic. All right. What next? The sum of squared errors. Q is equal to sum, oh just a sec, D is equal to diag of D. Extract the diagonal elements. Okay, Q is equal to sum E dot exp2 in the second direction. That's it. All right. So I have extracted the sum of squared errors. I have also gotten the Hotelling's T square statistic. Yes or no? Are you with me till now? All right. If you're with me, then we'll go further ahead. Now we are going to subject the test data to the same treatment. Okay. So T for the test data, the scores for the test data are X scaled test, XTS था, XST था, XTS star V all comma 1 2 3. E for the test data is equal to T test star no XTS minus T test star V all comma 1 2 3 transpose D for the test data is D is equal to this. For the test data is D for the test data is equal to T for the test data times singular values which are there. ये बात हजम हुई? And then I'll take a diag of that. And Q is equal to this. It's just that I have to do it for the test data. All right. Now subplot 2 comma 1 comma 1 bar D test subplot 2 comma 1 comma 2 bar what? Bar Q comma Q test. you can see okay, the way the data was generated, you can see the t square statistic, the Hotelling's t square statistic is below 0.05 for all the 200 data points. Okay, the first 30 data points in the test set, there are a total of 50 data points in the test matrix. The first 30 were generated in the same way in which the 200 data points were generated. So the correlation structure is not violated, and therefore the scores are in the nominal operation. Okay, the last 200 and the last 20 points were generated randomly. Randomly means no correlation structure whatsoever. Okay, and therefore you can see that in the last 30 structures the t square statistic is large. Okay, also more importantly the q statistic is large. The sum of squared errors is large. Sum of squared errors being large implies that the last 20 points are not following the correlation structure of the nominal data. Does this make sense or no? And if you want, we can sort of, well, there are too many data. This is a 10-dimensional problem, so you can't really see it. But let's just see. Plot x scaled all comma 1. This is the sorry CLF. CLF plot x scaled all comma 1. This is the nominal data. This is the variation in the nominal data. After principal component analysis, after x has been projected onto the principal components, whatever is left is in the errors. So let me also plot the error in the first column. In the first column of, okay, so plot, hold on, plot error all comma 1, let's plot it as red. You can see most of the data is explained. After projecting onto the principal components, the unexplained variation in x that remains, which is in the errors, which is in the residuals, is actually only this much, almost 0, right? Similarly, you can do it for all 10 components. Now let's just do it for the test data. Plot E for the test data x t s all comma 1. Hold on, plot E for the test data in red. Let's just see this. This is the variation in the test data. After project, you can see in the first 30 points, the residuals that are remaining are very small, red. But after the 30 points, the residuals are actually quite large. You see that? Huh? That is the t square. The scores are coming large because these are also large. You see, in the test data, the variability should be between -2 and 2. The t's are large because the variability goes up to 10. So therefore, the projection is also large, and therefore, if you remember the Hotelling's t square plot, the last 30 points, the t square was also large. That's because the variability in the x itself is large. ये बात हजम हुई कि नहीं? हाँ? Okay, so what? So well, that's that. Now you're just seeing. So the residuals are large, and I can also plot, for example, plot t all comma 1 versus t all comma 2 circles. Let's just look at, oh sorry, CLF. You can see it's a spherical type of distribution. On the other hand, if I plot xs all comma 1 versus xs all comma 4, I think this is the way I generated it. You can see there is a, the data is not really linear, not really spherical, and in fact the last 7 columns in the way I generated the data was I just generated as a linear combination of the first 3 columns of X. Okay, so therefore only 3 principal components came out, even though the matrix is 10 columns. ठीक है कि नहीं? And so on and so forth. Similar. So CLF plot T all comma 1. Hold on. Plot T all comma 2 red. Hold on. Plot T 1 to 30. 1 to 30 magenta. You can see the scores. The scores are within range. The reds are what are falling out. Okay, these correspond to the last 20 data points. I can also do this for T1 versus T3. CLF plot T1 to 30 all comma no. CLF plot T all comma 1 versus T all comma 3. Hold on. Plot T all comma 1 T all comma 1 and plot it in red. Hold on. Plot T 1 to 30 1 to 30 in magenta. Again you can see here most of the scores are okay. Okay, nothing see, suppose you draw a limit around T1 and T2. If you draw an ellipse around it, that usually my data lies in this regime, 99% confidence limit or whatever you want to call it, then you will see that most of the data is similar to my nominal data, except maybe ये थोड़ा सा बाहर चला गया, ये थोड़ा सा बाहर चला गया. Do you see what I am saying? ठीक है कि नहीं? Okay. In the errors, of course, you could see that the errors were large, much larger than usual. Okay. So large errors imply the correlation structure that was being followed in the original data and which was captured in the principal components, that correlation structure is no longer being followed. Okay, I hope this much is clear. And I hope you also understand how to get T square, V square, blah 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 blah. Okay, and how to do principal component analysis, how to get the scores. What would principal component regression be? You regress the scores with something that is to be predicted. Why? What is regression? X transpose X inverse X transpose Y is the regression coefficient, right? And that is how you predict. Okay, ki nahi? Yes or no? Okay. Now let us do it on the other data set, CLF. Load PCA data 2, I think. Just a second. Clear all. Load. I think tomorrow it's going to be like this. क्या करें यार? One has to live with it. Okay, so there is the X data and there is the test data. Okay, so again mx is equal to mean of X, Sx is equal to standard deviation of X, m comma n are size of X, X scaled is equal to X minus 1's m comma 1 star mean, oh sorry caps lock हो गया यार, mean dot divided by 1's m comma 1 star Sx. अबे यार क्या हो गया साला? अच्छा mx हो जाएगा यार वो. This had to be mx. I made it m. That's the problem. No, it's okay. Okay. So this is the mean centered unit variance data matrix. Okay, unit variance of every column. Every column has 0 mean and unit variance. All right. Now I do u comma s comma v is equal to singular value decomposition of xs, and then I say bar diag of s, and well, this is what I get. There are 3 columns in the data set. 2 principal components are significant, the other is insignificant. So actually, really speaking, your data matrix is actually your 3 dimension. So you're measuring 3 things, 1, 2, 3. These 3 things can actually span the whole space, 3-dimensional space. However, they are only spanning a plane. What is that plane that is being spanned? What is the plane on which these data points lie? Principal component 1, principal component 2. Okay, you can also actually plot the principal components. So I could say bar v all comma 1 to 2. What are the principal? Well, these are the principal components. Principal component 1 is sort of an average of 1, 2 and 3. You know, same amount, 0.6 amount of A, 0.6 amount of B, 0.6 amount of 3. It's sort of an average of all 3. And principal component 2 is B going in opposite direction of 1 and 3. Or 2 going in opposite direction of 1 and 3. So let's see. How did I generate this data set? I had generated this data set by, I actually don't remember. दो रैंडम कॉलम ले लिए, फिर उसको घुमा दिया, फिर इसको इसके बराबर कर दिया. I think that's what I did. So x1 is equal to x3 was one of the things. Okay, and where did this come from? I think this comes from the rotation that I did. It's hard to interpret, but if you put enough mind, it can be interpreted. You will not be required to interpret the loading. These are called principal component loadings. Okay, I am plotting the principal components themselves. Okay, these are called principal component loadings. You can always interpret these loadings as what is that linear combination of x1, x2, x3. Principal component 1 is equally weight 1, 2 and 3. Principal component 2 is these two moving together and the other moving in the opposite direction. Right? So that's how you sort of look at it. So now T score is equal to xs star v all comma 1 to 2, because I am retaining only 2 principal components, right? E is equal to xs minus xs star T star v all comma 1 to 2 transpose, right? I can do this to the test data also. So let me just do it. Size of xt 20, the 20 data points. I think 10 are normal, 20 are 11 to 20 are abnormal. We'll find out. Let's see. Okay, so xt scaled is equal to xt minus 1's 20 comma 1 star mean of x dot divided by 1's 20 comma 1 star sx. So now I have scaled my test data the same way as I scaled my training data, and I say the score for the test data is equal to xts star v all comma 1 to 2, right? Then I also say that E for my test data is equal to xts minus t star v all comma 1 to 2 transpose. अरे साला ये क्या कर दिया यार? Oh, I am so sorry. tt होना चाहिए था. Scores for the test data. I was using scores for, so my matrix dimensions are screwed up. Yeah, this is fine. Okay, so I've gotten the scores, I've gotten the residuals. Now let me get my hoteling statistic and the sum of squared errors. So D is equal to diag. Okay. Yeah, so this is fine, right? dt is equal to, yeah, this is also fine, 1 to 2, sorry. So I've gotten the Hotelling statistic for my test, for my training data, and also for my test data. Q is equal to sum of this. Q test is equal to, fair enough. All right, now let's just do it. Subplot 2 comma 1 comma 1 bar d. Let's say bar d and dt. Subplot 2 comma 1 comma 2 bar so okay, you can see that, well, if I draw a limit over here, see, this is what my nominal data is up to 200. Okay, if I draw a statistical control limit, it will probably come at 3 times of this, so maybe 0.15. You can see maybe 1 or 2 Hotelling's points are out of range. You can see in terms of the errors, up to 210 errors are small, 211 to 250 errors are large, 211 to 220 errors are large. So last 10 data points, the correlation structure is somehow getting violated. How do we see it? Let's do some plotting. See, this is a 3-dimensional problem, so I can make a 3D plot and then sort of, aise dekho, and see if it's lying on a plane or not, blah blah blah. Okay, so let's just do it. So plot x s or plot 3 होगा, sorry, plot 3 xs बचता है क्या? Shit, sorry, xs all comma 1 comma xs all comma 2, sorry yaar, xs all comma 2 comma xs all comma 3. All right, इनको प्लॉट करो एज अ सर्कल. Okay, let's just see. ये बन गया. Now I can rotate it in whichever way I want. So this is my nominal data. I'll also plot my, hold on, plot 3, and this time I'll say xts. Let's just say they are all red. Then I'll also plot 3 1 to 10 as magenta, which let's just see. साला ये क्या हुआ? नहीं यार, कुछ गड़बड़ हो गई. ओके, लेट्स जस्ट घुमा के देखते हैं यार. You see this? The data is lying on a plane. I'm looking in the direction of the plane. There are points that are away from that plane. So all of the data is lying on the plane. My first 10 data points, 201 to 210, first 10 test data points are lying on that plane. But the last 10 data points, 211 to 220, they show large deviations from the plane. Can you see this or no? So large sum of square errors denotes breakdown in the correlation structure. The data was supposed to lie on this low dimensional surface. It's actually not lying on that surface, it's lying away from the surface. So therefore the errors are large. You saw some of the scores were also large. That's because some of these points, even though they are lying on that plane, they are, if the nominal data lies in this much space, it's lying slightly away, therefore the scores were also large. Does that make sense or no? Huh? So this in short is principal component analysis. कोई शक या सवाल? I think I'm going to close the movie because last time it didn't get made for whatever reason.